Now we're going to talk about energy and types of energy. So categorized into two basic categories. There's potential energy and kinetic energy. So what is potential energy?
Unburned fuel.
Okay, that's an example. Okay,
Energy.
you guys are full talking, so I think Mackenzie's first. So
Amount of energy the object can release at some point in the future.
okay, so I'm sitting here and I could go for a run. Right? Okay. So that's my potential. I could when I'm running, that's my kinetic energy, right? Now, you're faster than me. Can you give me some of your speed?
I could try,
Would it work?
probably not.
No, because my mass only has a certain amount of energy and I can't take it from you. So, so I have a couple of videos that I thought were kind of fun. So these are, some of them are kid videos, but pretty good. So share those with you.
In this video, we will learn about energy. What is energy? Energy is defined as the ability to do work, which is when a force is applied to an object and it moves. Energy is divided into two types: potential energy and kinetic energy. Potential energy is the energy stored in an object. Kinetic energy is the energy that a moving object has. How is energy measured? Energy is measured in joules. Potential energy is the energy an object has because of its position relative to some other object. In a slingshot, the potential energy is stored in the object being flung. Forms of potential energy: chemical energy, elastic energy, nuclear energy, and gravitational energy. Chemical energy is energy stored in bonds of atoms and molecules. A battery stores chemical potential energy, which is converted into electrical energy. Elastic energy is potential energy stored as a result of deformation of an
This one's
elastic
not
object,
A
such
representative,
as
but
the
you look on
stretching of a
135.
spring or a rubber band. Nuclear energy is the potential energy found inside the nucleus of an atom. Gravitational energy is the potential energy of position or place, like a rock on top of a hill and curl on top of a slide. Kinetic energy is the energy possessed by an object in motion. Forms of kinetic energy: mechanical energy, thermal energy, light energy, electrical energy, and sound energy. Mechanical energy is the energy of an object due to its motion or position. The sum of an object's kinetic energy and potential energy, like a moving car and a windmill. Electrical energy is caused by moving electrical charges called electrons. Thermal energy is energy that comes from a substance whose molecules and atoms are vibrating faster due to a rise in temperature. Light energy Radiant energy is electromagnetic energy that travels in transverse waves. Sound energy is the movement of energy through a substance in waves. The law of conservation of energy states that energy cannot be created nor destroyed. However, it can be transformed into one form to another. No energy is lost. It is always conserved. Chemical energy from food is converted into mechanical energy. Chemical energy from batteries is converted to light energy. Electrical energy is converted to heat energy. Chemical energy from fuel is converted into mechanical energy. Light energy from the sun is converted to chemical energy through photosynthesis. Mechanical energy from a moving windmill is converted to electrical energy. Electrical energy is then converted to light energy. So again, energy is the ability to do work. It is divided into two types: potential energy and kinetic energy.
Okay. So what is potential energy?
Energy.
What's that?
Energy that's more for later.
The amount of energy an object can release at some point in the future. What's kinetic energy?
Like the energy that counters.
Does wood in a structure that is, it's releasing heat, does it have kinetic energy?
Yeah,
Yeah, and why is that?
because the molecules are moving,
Exactly.
they're just creating.
Very good. So we think of it as the wood's not moving, so that's not kinetic energy, but the molecules in the wood are, so that is kinetic energy. Okay, so heat of combustion, that might be one of your terms, the heat energy available for release. And what is combustion?
Rapid oxidation.
And the rate at which fuels release energy depends on what they're made up of, right? So is it wood, is it styrofoam? Is it your jeans? So how the fuel is arranged, how dense is it? So what's gonna burn faster and easier? A tree that's this big around or a tree that's this big around? Yeah, the little one, why is that?
Surface.
So it will absorb less heat than a big tree. And then the whole thing will then be able to raise to the temperature that we need for ignition. Then also, is there oxygen? We have okay, probably we open up for me. Okay, so here, I'm gonna light our candle again. Okay, what do I have here of my fire? Good heat, right? What do I have going on here?
Yeah, heat.
Okay, so I introduced heat. Okay, I've got oxygen. Thank you.
You have a producing agent or a fuel.
Okay. And then what is the fourth component in the tetraheters? Which, just let me say it already.
A chemical chain reaction.
Okay, so I got that going. Now. Put a lid on this. What happened?
Away the oxygen.
Yeah, so I took away the oxygen, so it's not gonna burn. Okay. Try it again. Okay. So. When I. That. Do that. Okay, it reignited. So, at that point. With the lid off, it couldn't burn because it didn't have enough oxygen. Opened it up, had that ignition source, and it relit. So we think about that. In a fire, we're gonna talk about the how it applies in structure fires. We have a room or a building. And the fire's been burning and it's a well-sealed room. Fire has gone out because it has consumed all of its oxygen. And what happens if we open up the door? It gets that, so you think of it like somebody who's not breathing well. We give them oxygen and it opens everything up, okay? So just like a fire, it starts to breathe again once we introduce that oxygen. So I'm gonna do another experiment here, but I need somebody to grab me a little bit of water. Just grab it out of, actually I got a little here, but just fill that up with water. Okay. Thank you. Oh, that's nice. It's gonna be really fun. Great. Okay, you guys can come closer. Okay, so we're applying heat, getting those molecules to move, turning it into a gas. Right? So now we are burning. So it has what, 4 parts? Heat, fuel, oxygen, okay. So now. Put this up in the top. See what that thing's trying to do? It is starving, it wants that oxygen, so it's trying really hard. And so it creates that as it's. Have you guys heard of like a backdraft? Yeah. And so what's happening is it's trying so hard to find that oxygen that it's pulling. And so like you'll see, if you see like under a door or in a window, sucking the air in, it's trying to get that oxygen. So then if we introduce that oxygen, it's off to the races, right? You guys want to see it again? So it's burning just fine. If we had other fuels around it, it's preheating those are off gas. It would ignite those fuels, so this fire would be getting bigger and bigger and bigger. Right here, we're limited on fuel, so it's gonna stay about the same size. Okay, now I'm gonna get rid of that oxygen. So it's consuming, you can see it's struggling a little bit. Suck that right up. Okay. Science is cool. Look at that, it has sucked so hard. That it has pulled that. Anybody else want to try it? Yeah, you guys are good. Okay. All right. Make sense? Okay. So when we have fire, you're always gonna have 2 things, right? What are those things? What is? Okay, so you have.
I got.
Okay, and maybe that was kind of a poorly worded question. So 2 things are gonna So we're at the campfire. It's a cold night up in the mountains. We're sitting around the campfire. What do we feel? Heat. And what is the heat a result of?
Formation of new bonds.
So the chemical reaction is releasing heat. And then what do we see? Light.
Light.
Yeah, so you're gonna have light and you're gonna have heat. Here's another, this is a shorter video, but I thought it was worthwhile. Has some stuff that we don't talk about in the book. So
Learn and play online. Forms of kinetic energy. Please check out our other videos that explain what energy is and the different forms of potential energy. Now let's start this video with a quick recap. Energy is the ability to do work. The different forms of energy can be described as either being potential energy or kinetic energy, and today we will be exploring forms of kinetic energy, which include mechanical energy, thermal energy, electrical energy, sound energy, and radiant energy. Kinetic energy is moving energy, and the first form of kinetic energy we will look at is mechanical energy, also known as motion energy. Mechanical or motion energy is energy that we can see because it is simply the energy of motion. It doesn't apply to just living things like us. Machines have motions too. Take this robot, for example. It is demonstrating kinetic energy in the form of mechanical energy as it moves. Here is another example. The ball is static at the moment. It possesses potential energy, which means it has stored energy until a force comes along to move it. Once the ball has been kicked, that potential energy transforms into motion energy as it flies across the field and into the goal. Moving on to the next form of kinetic energy is thermal energy. Thermal energy is also commonly known as heat energy, and it is when there is a rise in temperature and an object produces heat as a result. Now you may be wondering why thermal energy is considered as a form of kinetic energy. That's because the atoms and molecules contained in objects that produce thermal energy are moving at an incredibly fast rate. You can't actually see the atoms or molecules because they are the tiniest cells or particles of an object. But if you were able to see the movement of the atoms and molecules, it would look similar to this when thermal energy is present. The hotter the object or heat produced, the faster the movement of the particles will be. The next form of kinetic energy that we will discuss is electrical energy. Our modern day lives are dominated by electrical energy. It has become a crucial part of our everyday activities, from television to iPads to cooking appliances and lights in our homes. Just like thermal energy, electrical energy is a form of kinetic energy, even though we cannot see it moving. We know that electrical energy moves though because of the results of what it can produce, like light and heat. Electrical energy is a result of electrons moving around a circuit and providing electrical power to gadgets, devices, and machinery that need electricity to work. The electrons are constantly flowing and only stop when there is a breakage in their path. So when you turn off an electrical device, you are breaking the path for the electrons to flow, putting an end to the electrical energy it needed to operate. Did you know that lightning is a natural form of electrical energy? Lightning strikes are extremely dangerous and can even be fatal for us humans if we are ever struck by one. Let's now move on to the next form of kinetic energy, sound energy. Sound energy is energy that we can hear, and it is produced through vibrations of matter. It travels through other matter like water or air. And it moves in the form of waves. Think of sound energy as a domino effect. Once a sound is produced, the vibrations bounce from one particle to another, whether it's traveling through water, air, or gas, and it keeps going until the sound energy weakens and eventually stops. Now we've reached the last form of kinetic energy we will explore today, which is radiant energy. Radiant energy is a form of what's known as electromagnetic energy. It is described as a form of kinetic energy because the electromagnetic radiation, which is made up of tiny particles called photons, move in the form of a wave. There are different types of radiant energy, including X-rays, gamma rays, radio waves, sunshine, and light. Light energy is the only form of radiant energy that is visible to the human eye. The wavelength of the photons depends on the type of radiation being used. For example, radio waves have low energy photons, while X-rays have higher energy photons. Even though we cannot see electromagnetic waves besides the photons used for light energy, radiant energy is a part of our everyday lives. The electromagnetic waves transform kinetic energy into other forms of energy that we use, including microwaves, television, communication, and medical imaging.
Thanks for watching. Please remember to subscribe for more videos.
Okay, so we understand potential energy and kinetic energy. And then more science stuff. So measured in joules. And the SI is the International System of Units. And so what it is, the quantity of heat required to change the temperature of 1 gram of water by 1 degree. More joules. What does that mean to you?
.2 joules.
But if something has more joules than something else, what does that mean to you?
It's hotter.
So, how is energy, I think how to ask this. What is heat? You guys can.
Is it when the molecules start working faster and moving faster, and it creates I believe it's thermal energy, and that produces heat.
Yeah, so the heat is, if you guys turn to 191.
Form of energy associated with the motion of atoms and molecules within a fluid, which is transferred from one body to another as a result of a temperature difference in the bodies. Such as from the sun to the earth, to signify its intensity, it's measured in degrees.
Okay. All right. So what's gonna be burned hotter? A toothpick or a log? Log. What's gonna make you warmer if you sit warming yourself by a toothpick? Or by a log? Yeah, why is that?
Has been fast.
Got more energy.
Mine,
I was thinking faster.
What's that?
I was
It
thinking
will burn
faster.
faster because of its surface dimensions. All right. Now there's two types of reactions. Exothermic and endothermic. So we think of fire as an exothermic, so it's releasing heat, right? And then endothermic, sucking the heat into its body. Okay, so here they list water because water is really good at absorbing heat, so it's bringing in, and the fire pushing out. There's some other types of endothermic reactions. I don't know if they're listed in your book, but when it relates to firefighting, we use water because it is so good at taking that heat out of the fire. Just sucks in, absorbs that heat. So why do we need to know about potential energy and kinetic energy when we're thinking about fire?
well,
Like, you want to say something?
if you got a structure fire, you gotta know what's in it, like what potential energy you go.
You need to understand both those factors to be able to adequately assess and perform operations on fire.
All right. We talked about the fire triangle and the fire tetrahedron. What is the one difference? Chemical reaction. What are some of the common chemical reactions you observe? Every day. Cooking.
You start.
What's that?
When you start your fun.
Starting your car. Drinking.
This, well, no, that would be a physical reaction. I was gonna say that the steam that comes off the coffee, but that's a physical reaction.
There you go, that's good. We talk about ignition and combustion. All right, so we've learned this, right? That it's not the solid that burns, it has to turn into a gaseous state in order to burn. So pyrolysis is what we see in fire, right? And then vaporization is when it's off gassing in the liquids. So when you were talking about your coffee and the steam, that's off gassing of your coffee. We've got a couple different types of ignition. So got piloted ignition. You guys have heard of a pilot light? We have heat source that comes in and lights it, right? Would this candle ignite by itself? Probably not. There are some things that do what we have to say is auto ignition. Some people refer to it as spontaneous combustion. In the wildland world, you guys use linseed oil, right? And so what did they always caution you when using the linseed oil?
Rice
Hopefully
catching
they
fire,
cautioned you. What's that?
rice catching fire, if they're wadded up.
Exactly. So when you were doing your wildland stuff, did you use the linseed oil on your tools, your handles and stuff?
We did, and then afterwards we just keep, like, either put the rag in a cool place or wash it off so that it wouldn't.
Perfect, yeah. So, because, go ahead.
I was saying like haystacks catching on fire, the auto ignition.
Mhm. Yeah, there's a chemical reaction that produces enough heat. It ignites. Let's see. I've got a video in here and I can't remember where I put it in. Okay, so when we have a fire in a house, we talked about it a little bit over here. So I have in my bedroom, I had an electrical problem that generated some heat. Ignited flammable materials, right? So I caught the curtains on fire. Does it stay on the curtains and go out?
No.
No, what's happening? What happens next?
Travis, right?
It heats other surfaces, so then that way it can produce more gas.
Okay, yeah, so it heats the stuff around it. Those off gas. We have an ignition source. And then it starts that burning process. And so what do we need? What kind of reaction do we need for that fire to go out?
You need to be missing one of your 4 elements of the fire.
Okay, so what do we use in the fire service?
Water.
Okay, and how does that work? You want to say it, don't you?
It removes the heat.
Okay, and what kind of reactions?
It absorbs it, so that
Okay,
it's.
what kind of reaction is that called? Yeah, endothermic. So, endo, I think of N2.
So I guess I've got a question about that. So it definitely, so water takes away the heat element of a fire triangle, but what about taking away the oxygen as well?
Yeah, so you remove the oxygen, fire goes out.
But do we also see that water, well, obviously water does take away oxygen to a degree. Because if you have a significant enough of water on an object, it could also.
You smother it, yeah, and so, yes, it could work that way, but. In our world, it's usually the endothermic reaction where we're absorbing the heat, taking that part out of the tetrahedron. Okay. You can do things like, sometimes like foam will disrupt that chemical reaction and take out that part of the tetrahedron. Where was going? Okay, so we're using water to absorb the heat. But if we don't, the fire goes unchecked. Like you said, it is heating the things around it. Those are off-gassing and those are burning. Now there's a piloted ignition and then there's auto ignition. Why do you think that the auto ignition is always higher than its piloted ignition temperature?
You're applying heat with a piloted, where an auto, you're not applying the heat, it hasn't generated heat.
And then its own heat, yeah. And so if I have this candle, so I apply my piloted ignition and heat up that that fuel, it turns into a gas. How hot do you think it would be if this ignited by itself? Pretty darn hot, right? Just like those rags. By themselves. You know, I could apply the piloted ignition, it would ignite, but at a much higher temperature, that chemical reaction is going to ignite those rags. Does that make sense? All right. So what is off-gassing in a solid?
Pyrolysis.
Okay, what is off-gassing in a liquid? We've got two types of combustion. Self-flaming combustion and non-flaming. So what do we think of as non-flaming? What is a common term for that?
Smolder.
Smolder, yeah. So, in a flaming combustion, we're gonna see the flame above. That's those gaseous fuel mixtures. We got the ignition. And then where the non-flaming is gonna be that smoldering where you don't see the flame above it. So how does it work? You have your ignition source, and your heat, you got your oxygen coming in. And then you have your fuel. And then it's pushing out those combustion products, right? What kind of reaction is that? Is that
Exothermic.
exothermic? It's pushing out. Endo? It's open burning. It's got plenty of oxygen. It's just gonna run off to the races, right? We talked about that in one of those videos. Where does the fire go? Because what? Fire's trying to move from. Okay. So that's why we say heat rises.
Thermal layer.
What's that?
Thermal layer.
There will be thermal layers. We'll get into that. So we talked a little bit about the non-flaming combustion, so smoldering fire, you think it burns slower? And it's right close to that, the fuel surface, right? So you think about like in a, you go back to your campfire, what's gonna burn faster, a smoldering log or a flaming?
Flaming.
Flaming. Okay, so products of combustion are heat and smoke. Is smoke flammable? So, but is heat dangerous to us? Yeah. Because you don't want to breathe superheated gases and you don't want to be touched by the. The heat. Okay, so smoke made up of gases, vapor, because why is that? So combustion. With that,
Incomplete combustion.
and then you also have your solid particulates. And we talked about when wood burns, what does it break down into?
Carbon monoxide, dioxide, H2O, water.
So why do we see so much smoke in structure fires?
The different types of materials, some materials burn at higher temperatures, which maybe the fire hasn't gone to that point. So all those unburned fuels are turned into smoke, and they go up.
Yeah, and so what happens as that is moving, the hot, yes, and stuff they're moving, and so they're gonna pull with it some of those particles, right? And so, do we have to worry about this? How about if this is in here? Yeah. So you can see right here, is there wood? Are there structural members in there? Okay, so this is the roof. Are we burning beams? And yeah, I see, Esteban shaking his head, no. Okay, so what's burning here?
The smoke.
The smoke is burning. So we've got two fuel types, natural, which would be what? Wood. An untreated wood. Potentially cotton, things like that, and then synthetic. What are some of examples of synthetic materials?
Polyester.
Was that? I can't hear very well, so.
Polyester.
Polyester, okay,
Polymers. Fiberglass insulation.
what are some of the byproducts?
Hydrogen cyanide.
The bad for us? What else? What else?
I'm about to say them. Poly something.
So, yeah, the polymers, so the polyurethane, polyester, polypropylene, polystyrene. Stuff that makes up our couches, our cushions, our carpets, all of that stuff. It's gonna off gas. Do you remember a few weeks ago, we watched the Toxic Twins? And it was really bad for us, right? And what are the two that make up the Toxic Twins?
Carbon monoxide and hydrogen cyanide.
And do you remember how those work?
The hydrogen cyanide bonds with your blood and it prevents your blood from using oxygen, so it, or is that the other?
I thought it was the other way.
Yeah.
So carbon monoxide is favored by your body's blood cells, and so when it goes into the lungs, they take up the carbon monoxide and then it's distributed out in the body as oxygen.
It bonds to it more than oxygen will, like it
Has a
to
higher
your blood,
affinity.
it bonds to your blood more than oxygen will, it's like more favorable, it's higher.
They're both really bad.
So like it'll win over oxygen,
And then hydrogen cyanide
kills organs.
goes into your body systems, and yeah, it bonds with your body's cells to prevent them from uptaking either carbon monoxide or oxygen. And so, like, because I remember they said hydrogen cyanide attacks the organs and carbon monoxide attacks the blood.
So fires have a limited air supply. So if you don't have, so they don't have all the oxygen they need. So they're not gonna burn efficiently, right? And so. What are you gonna see? So if it's not burning efficiently, you're gonna have incomplete combustion, right? Which is gonna produce what? What's that? More smoke, yeah. And so then if you give it all the oxygen it needs. It's gonna be more of a clean burning. Okay, so this is in your book on 140. These are all things that we will encounter. I'm not gonna go too far into this because we've covered it. Now, what's the problem with carbon dioxide? We have it in our the air we breathe, right? So when does it become a problem for us?
It's too much.
Yeah. So and because it works out, it'll
push oxygen out.
how much oxygen do we need?
20%.
Yeah, that's right, 100%. So you start dropping below 19, then you're gonna start having some issues there. You guys go to medic school, you start to understand the whole process. You get too much carbon dioxide in your blood and what happens there. Okay, a lot of bad stuff in smoke. So don't breathe it.
Gotcha.
Okay, how do we know if it's flaming or non-flaming?
Well, if you see flame.
Yeah, there you go. If you see a flame, it's flaming.
There's light present.
They'll both have light and they'll both have heat. So think of like a charcoal. So it's producing some light, producing some heat because we burn our or we cook burgers over charcoal, which is smolder, non-flame. You can also burn it or cook it over. I'd say burn because that's how I barbecue. Burn it. But, you can cook it over flame. Okay, so we are going to take another break. You guys want to?
When you're operating on the fire ground, it's important to understand that high pressure gases flow to low pressure. This is a basic fire dynamics principle that explains why ventilation works. As a fire develops in a compartment, the heated products of combustion expand, creating an increase in pressure. When you make ventilation changes to the structure by opening a door or taking a window, you're creating a new low pressure and a flow path. A flow path is the areas within a structure where heat, smoke, and air flows from an area of higher pressure to lower pressure. It's composed of at least one intake vent, one exhaust vent, and the connecting volume between the vents. This flow path can be used for your tactical advantage, such as indicating the location of the fire for the advancing hose crew, or to your detriment as hot gases flow from a bedroom fire to a door, passing over your search crew, forcing a retreat. Here's an experiment that's an excellent example of fire flowing from high pressure to low pressure during different stages of the fire. We ignite the fire in the living room on the first floor of this two-story townhouse. As that fire increases in size, the temperature increases, which increases the pressure, which has the products of combustion flow out of that second floor window that's halfway open. You'll see light smoke start to come out of that second floor window as that first floor pressure increases. That window acts as the low pressure and will continue to do so until the fire on the first floor runs out of oxygen. Once the fire on the first floor runs out of oxygen, It's gonna change the pressure. It's gonna be looking for oxygen, so it's going to try and pull oxygen from around the front door. You'll see the smoke puffing at the front door. When it can't get any oxygen through that front door, the temperatures are gonna decrease. As the temperatures on the first floor decrease, the pressure decreases. As that pressure decreases, it's actually gonna go into a negative pressure. As you see, no more smoke is coming out of that second floor window until the first floor door gets open. Once that door gets open, creates a new flow path. Air goes in the lower half of the door, hot gases come out the top half of the door. And as that fire begins to increase in size, you also get those gases flowing up that second floor to the low pressure out of that bedroom window, leading this fire to transition to flashover.
Do you want to see that again? Okay. Be valuable.
Well, it explains why ventilation works. As a fire develops in a compartment, the heated products of combustion expand, creating an increase in pressure. When you make ventilation changes to the structure by opening a door or taking a window, you're creating a new low pressure and a flow path. A flow path is the areas within a structure where heat, smoke, and air flows from an area of higher pressure to lower pressure. It's composed of at least one intake vent, one exhaust vent, and the connecting volume between the vents. This flow path can be used for your tactical advantage, such as indicating the location of the fire for the advancing hose crew, or to your detriment as hot gases flow from a bedroom fire to a door, passing over your search crew, forcing a retreat. Here's an experiment that's an excellent example of fire flowing from high pressure to low pressure during different stages of the fire. We ignite the fire in the living room on the first floor of this two-story townhouse. As that fire increases in size, the temperature increases, which increases the pressure, which has the products of combustion flow out of that second floor window that's halfway open. You'll see light smoke start to come out of that second floor window as that first floor pressure increases. That window acts as the low pressure and will continue to do so until the fire on the first floor runs out of oxygen. Once the fire on the first floor runs out of oxygen, it's going to change the pressure. It's going to be looking for oxygen, so it's going to try and pull oxygen from around the front door. You'll see the smoke puffing at the front door. When it can't get any oxygen through that front door, the temperatures are going to decrease. As the temperatures on the first floor decrease, the pressure decreases. As that pressure decreases, it's actually going to go into a negative pressure. As you see, no more smoke is coming out of that second floor window until the first floor door gets open. Once that door gets open, creates a new flow path. Air goes in the lower half of the door, hot gases come out the top half of the door. And as that fire begins to increase in size, you also get those gases flowing up that second floor to the low pressure out of that bedroom window, leading this fire to transition to flashover.
Go ahead.
So, when the fire transitions to negative pressure, does that mean that it could mean one of two things in my mind? It could mean that it's burning cleanly enough because it's getting enough oxygen that it's not smoking, or it could mean that the fire has diminished in size and severity. So which one kind of tends to happen when you have negative pressure?
You're gonna run out of oxygen.
Okay.
I mean, you think of like the modern homes, we got a lot of stuff. Okay, so there's plenty of fuel. We're gonna run out of oxygen before we run out of fuel. And so like we showed over here, that negative pressure, what's it trying to do?
Try to suck.
It's trying to get oxygen. So it's out of oxygen, so it creates that negative. So it's sucking that in, okay? And so that's what's happening there. It is out of oxygen, it's trying to get that oxygen.
Okay.
And then you saw as soon as they opened up that door, it was almost instantaneous what happened upstairs, right? So you see the bottom floor, you see the top floor. We give it oxygen and it's got what it needs. It's like, I can breathe. Yeah. Okay. Makes sense.
So at that point, the fire is probably smoldering, or it's still maybe got the heat in it to continue the reaction, but it's not really flaming.
Right. And so sometimes you'll see, and we'll talk about this later in the chapter, but you'll see it goes into like maybe, what we call the decay stage. So it goes in, you'll see a dip here, and then as soon as we introduce oxygen, then it's off to the races again. Unless it's out long enough without oxygen, that it's start and it puts itself up. Doesn't happen very often, but there's a potential. Go ahead.
Okay, so then how long would it have to be in the decay stage to be able to introduce oxygen and not have it flash over?
Well, what do you think that would depend on?
How big the fires?
Yeah, so the amount of fuel and how much has been burning. And so, yeah, and how much has been consumed. So if you fully consume it, then you don't have much left to burn, right? Does that make sense?
Mhm.
Okay. Okay, and so here we'll see the cooler air come in, feeds that fire, and where's it gonna go? Up, and then what's this trying to do? Looking for a lower pressure. Why do we have the pressure increase?
Because of the size of molecules or because the vibration they
Yeah,
expand.
so they're bouncing all over each other, right? And so that gas is expanding as those are moving around quickly, right? And so then we think about too, on the other side. We think of bigger steam or an ice cube. Okay, and so the ice cube is compact. What's happening to those molecules? Yeah, they're a little more compact. They're not bouncing around until you start putting heat on them. So you put heat on that ice cube. What happens? Expands. You know, and then turns into water, and then you put more heat onto that. What is that process called?
Oh, I know.
Okay, but we've got pyrolysis. Vaporization. You can, it looks like you need to.
Yeah, sorry.
We increase the pressure there. Then your brain gets so full that all those brain molecules are trying to find lower pressure
And that's,
coming up to nose.
and that's an endothermic reaction?
Was it endothermic is when you're absorbing the heat, right? So it's taking the heat in. But vaporization, right? Wherein when we're converting it to gas is but like a solid is. Okay. I think we did that pretty good. All right, where are we at here? Okay. What's heat release rate?
What was that?
What is heat release rate?
Right, how much heat releases?
Energy release per unit of time.
Okay.
Fuel burns.
Okay. Expressed in kilowatts or megawatts. Anybody a Back to the Future fan? You know what? You know what I'm talking about?
I do.
So what's gonna affect your heat release rate?
Your fuel.
In what respect?
The amount of, well, so your amount of fuel and your density.
Oxygen,
What is that?
oxygen.
That's a component. So what's gonna have a higher heat release rate? A room that has a couch and a table, or a room that is a hoarder's house?
Order.
We've got a lot of fuel in there. So here, it kind of shows you, okay, so it makes sense that the heat release rate in a candle is gonna be a lot less than maybe something burning in a trash can, or maybe our sofa's on fire. Does that make sense? And then we also talk about, and I think we're gonna hit it here in a little bit, but the arrangement of the fuel. So I'm gonna refer you back to your definition page on 191. Who wants to tell me what heat is?
Heat is a form of energy associated with the motion of atoms or molecules within a fuel, which is transferred from one body to another as a result of a temperature difference between the bodies, such as from the sun to the earth to signify its intensity. It is measured in degrees of temperature.
So heat is a form of energy. We talk about heat transfer. Tell me some examples of like a heat transfer.
A wood fire stove getting hot because it has a fire inside of it, or it has a combustion reaction.
So it's transferring from the fire that's burning pellets or wood, right? And it's going to where
It's transferring to the metal of the stove.
Okay.
So it's heating up the stove.
will that stove get hotter than the fire?
No.
And what is temperature? Yeah, it's a measurement of heat. Different scales. Here we talk about the Fahrenheit. So you'll see in your book, there's a lot of definitions that are pretty similar. So they're the same but different. So like heat flux is a measure of the rate of heat transfer. So what does your, what temperature does your gear protect you to? Do you remember?
Your lowest rated PPE will protect you to about 300 degrees.
Yeah, a little more than that. And what part of your PPE is that?
That's your face mask.
Okay, so what's that?
You say lower or higher?
The lowest part of your PPE is your face mask. They say they're rated for about 400, but we've seen them fail below that. So when you're in a fire, the heat flux is the time from when you're like the transfer of the heat from the fire to your PPE, right? That make sense? Okay, so how long do you have?
Minute to 3 minutes ish, depending on the rate of heat transfer.
Well, it depends, yeah, so it depends. What's the heat release rate? So, do you have more time in a room that's hotter or cooler? Cooler, yeah. Let's see, let's pause for a second, I think. Are your brains getting saturated? What's that?
So I'm learning a lot.
Yeah, go on. I don't want to overload you guys. We talked about the different types of energy, right? what would be an example of mechanical energy? Was it? Ready? Ready? Yeah, I guess so.
Friction.
Energy. What would be an example of like chemical? Chemical energy.
A battery.
How about electrical? You don't have to be right, you just have to be confident.
A light switch.
A light switch, okay. How might any one of those create a problem that we are called to fix? So a fire problem.
Heat.
Okay. So what chemical energy?
Well, if you think about like battery, if battery goes bad or explodes to make an electric car, it's car tires.
Would you think that chemical energy is the most common source of heat in combustion reactions?
Yeah.
Makes sense, right? Okay. All right, electrical energy. That cause problems for folks that need us to come fix the problem?
Yeah.
Okay, awesome.
Short.
Yeah, it happens quite a bit. All right, now we're gonna talk about heat transfer. What are some ways of heat transfer in fire? Say it loud.
Convection.
Convection. And what is convection?
Transfer of heat by the movement of heated fluids or gases, usually in upward direction.
Okay, yeah, I saw you making that symbol. So what is this? This is moving air.
From high to
Okay, so in a fire, we're moving that hot air and hot gases. So convection is bringing that heat through the movement of air. We're not gonna see it through liquids in a fire. Okay, but that is another way that you can transfer heat is through liquids. But in our world, we're concerned about the convective, the travel of air. Okay, what is another way to transfer heat?
conduction.
Conduction, okay, and what is conduction?
Touching.
Yeah, so object to object. Okay. And then what is the last one? Radiation, okay. So sometimes we get the convection and radiation mixed up. And radiation is, we're not thinking like X-rays and glowing men, but. So conduction, I'm in a fire and I touch something and whoo, hot. Okay, so object. Radiation. The heat emitted from the object. Into the air. Okay. That's radiation. And convection. Heated up this air. And it's moving, okay, and then as this moves, it heats up the stuff around it. Okay. And then, I don't think I can draw. So what about if I put two hot objects together? Will there be conduction? Yeah, they'll exchange that heat. And like we said, this is 400 degrees, this is 200 degrees. Can this reach 500 degrees from this? No, it will only absorb as much heat as this one's putting out. Does all of this make sense? Does that make sense to you? Or you have some questions? It's okay.
So
take my
that
question.
wouldn't be conduction, it would be radiation.
So a conduction is object to object. Where radiation is the heat going right out. So, let's see. We've got. The heat is going from here to here. It's waves coming out of it. Okay. Where this is where a lot of people get hung up, the difference between radiation and convection. So now we've got. Okay, so we're gonna have hot and not hot. Okay, so the heat's coming off of this, and now we've got air here. That air is going to bring that heat with it. And as it's heating up the air is moving, it's bringing the heat with it. So convection is heating air or liquids, which will then warm the other stuff that it's coming in contact with. For radiation, it's just like right here, I'm gonna heat it by that, the heat waves coming off of it. And then conduction is object to object. It's just coming right off of it. Let's read the definitions, what the book tells us.
Conduction. Physical flow or transfer of heat energy from one body to another.
Okay.
Through direct contact or an intervening medium, from the point where the heat is produced to another location. Or from a region of high temperature to a region of low temperature.
So we look at conduction. What is conduction? What does it say?
Heat from one body to another.
So conduction is physical flow or transfer of heat energy from one body to another through direct contact. Or intervening medium, okay, so we're thinking object to object. All right, so we got conduction. Then we go to convection. What is convection?
Transfer of heat by the movement of heated fluids or gases, usually in an upward direction.
Okay. Then, how about radiation?
Transfer of heat energy from one body to another body through the intervening space by electromagnetic waves. Like,
So. If you know those, it should be golden. How do you think most of the heat is moved? Or how is most of the heat transferred in a fire?
Convection.
And we saw that in that house, right? Moved up, brought the heat, it wasn't radiating from that. I don't know what was on fire downstairs. Probably a pallet, because that's what we burned in training fires, but that pallet wasn't heating up the upstairs. It wasn't conduction, right, because it wasn't touching anything upstairs. And it had the radiating waves, that wasn't heating the upstairs. So it was as those gases heated up and moved from high pressure to low pressure, moved upstairs, and it brought that heat with it. And then we'll see as it, what happens when we bring heat. It heats up the area around it. Pyrolysis, more fire, bigger fire. Hey, is all that making sense? Okay. All right, on page 149, it talks about radiation, things that affect the ability to transfer heat through radiation. And what do you think those will be?
the
Distance, yes, for sure. What else?
The whatever your atmosphere is made out of.
Okay,
It's like, well, actually, no, not for radiant heat. Well, because radiant heat is the electromagnetic
Yeah, it's got your waves there. Those are, that's how I signify waves. Okay,
Yes, the intensity of what.
yes, for sure. Then how about the receiving object?
The surface.
The surface, okay, what it's made up of, right?
The temperature of that object.
Okay. So, okay, go ahead.
I have a question, so. It says the nature of exposed surfaces, right?
Mhm.
And it says that dark colored materials will emit and absorb heat more effectively. Why do some turn out gear, why is it black? Why do they choose to wear black?
I don't know. No, I think that's a totally legit question. There's controversy. Some people swear by it and some people say no. Say, for things like that, it can absorb heat. It also hides dirt, so. I would be an opponent of dark gear, but some people say, black is slimming, so you wanna look good. But, so you guys think about on a hot summer day, do you wanna wear a black shirt or a white shirt? A white shirt. What happens when you're wearing black? Kind of hot. Yeah, cause you're. It's so sweaty. Not sweating, but. It hides the sweat. All right. I think that is, you guys know what thermal saturation is? What is thermal saturation?
When it can't absorb any more heat.
And I think that our body are at maximum saturation, right? So let's pause for now. Go.